Welcome everyone. This energy band gap is the beauty of semiconductor. Metals do not have this energy band gap. Okay, and for insulators like glass, actually this energy band gap, this energy band gap concept will only come when the material is sort of crystalline. What is crystalline? Crystalline means no matter in what direction you look in a crystal, right? So I told you X, Y, Z. So these are the atomic arrangement in a lattice, right? So crystalline material means that no matter in which position of the lattice you go, it will always look the same, which means the arrangement of these atoms as lattice points are always the same. There is no distortion to this. Everywhere in all direction, they will always look the same. There is a continuity. There is no local variation of this. If somewhere it is like that, somewhere it is like that, it's not like that. It's all uniform, okay? And the atoms are arranged periodically. The atoms are arranged periodically, and this periodicity is not violated. So they are highly periodic in all direction. This is the crystal structure, and only a crystalline material actually has, you can define a band gap technically speaking, but even then qualitatively you can assign a band gap to insulators also. Okay, like say for example a piece of glass or a piece of like plastic or wood. They do not actually have a band gap, but we can qualitatively assign and say, or even oxide for example, you can take an oxide, for example aluminum oxide or silicon oxide. You can sort of assign a band gap to these materials, and this band gap actually for those materials, for these materials is very high. When I say very high, what do I mean? I'll come to that. Okay, this is very high. For semiconductor this is not so high, not so high. Okay, again high is a qualitative number. This thing we have to come up with some quantitative number. We'll do that. Okay, this is not so high for semiconductor, and band gaps do not exist for metals. Band gaps do not exist for metals. Okay, so what happens is that I told you this is now band which is fully filled with electrons, and this is a band which is empty. So what happens is that you can excite electrons from here, you can excite electrons from here to go there, another electron here to go there. What happens then? How do we excite them? We excite them by different ways, we will come to that. But if we can excite electrons from here to there, what will happen is that this band is empty, no? So whenever the moment the electrons are here, they can flow. They can flow under the application of a electric field. They can flow, and if they flow, they carry current. What does it mean? It means I can change the conductivity or the resistivity by what? By deciding how many electrons I send there. If I send more electrons, the current will be more. If I send fewer electrons, current will be less. If I send no electron, there will be no current. So that's how you tune. In metal this is not there, that's why you cannot tune. What happens in metal is that your actually in metal, we are not discussing about metal, but the highest field states, you know, this is the highest field state, for example, we call it some EF for example. This is actually, there is no band gap per se, but it is the electrons at the highest field states, they have lot of available states here. This is, you see, empty, so they can immediately transport, they can immediately carry current, they don't have to excite anywhere. The highest occupied energy state by electron actually exists in such a way that you have energy states here itself, you don't have to excite anywhere. And in insulator this gap is so large that from here, you know, that from here to excite there is almost impossible. It's very large gap, and that's why you cannot tune the conductivity. That is main reason of difference between insulator, metals and semiconductor. So in semiconductor you are able to tune it. Okay, in semiconductor you are able to tune the conductivity. That's the beauty of semiconductor devices. All right. So now I told you, let me use a good color here, right. So this is a fully filled band. You understand now how bands are formed, right. I told you 2s level is here, 2p level is here. As you bring the distance closer, they split, right. These are filled, and then this is a gap, this is empty, this is completely filled, this is the band gap, this is distance by the way. So as I am bringing the atoms closer, I get this splitting of the band, and that's how band gap is formed, right. So this is how energy band gap is formed, and this is how we come to this particular state, that this is filled. This particular fully filled band is called valence band, please remember. Okay, this is called valence band, and this is fully filled with electrons, so they cannot carry current. Why? Because electrons are completely filled, no? How will they move? For current to flow, electrons need empty states where they can move. Electrons need empty states where they can move to, and only then current will flow. If this is completely filled with electrons, then current cannot flow because electrons do not find any empty state to go. But the moment you excite one electron here, right, the moment you excite one electron here, this is empty, so that electron can now move, and that is why current can flow. So, electrons can only move here, technically speaking, and this is called conduction band, sorry, okay, conduction band. So, conduction band is this empty band where electrons can be excited. Valence band is this fully filled band where electrons cannot move, and the energy difference between them is the energy band gap. This unit of this energy we call electron volt. Do you know what electron volt is? 1 electron volt is how much? That 1.6 into 10 to the minus 19 joule. Remember? Electron volt is energy, not voltage, okay? And I told you 1 electron volt is 1.6 into 10 to the minus 19 joule, and this electron volt is the unit of energy for semiconductor band gaps and energies, okay. So, the electron, this is the band gap, for example, okay. Now, what is this gap in semiconductor? This is a gap that is not too large, I told you only, okay. Only then you can excite the electrons from there to there, no, only then you can excite electrons from here to there. So, that band gap cannot be too large. Now, what is too large, what is too small? So, typically the most commonly used semiconductor is silicon, okay. The most commonly used semiconductor is silicon, and silicon has an energy band gap Eg is equal to 1.1 electron volt. That is the value. That means silicon, this is conduction band, I call it Cb, and this is valence band, I call it Vb. This is fully filled with electrons. This gap is 1.1 electron volt, okay. You know 1 electron volt is this many joules, right. So, this is the gap between conduction band and silicon and the valence band of silicon. So, for you want to make silicon conducting, you have to excite electrons from here to there, okay. Only then you can conduct electrons to, right. So, this is the basic concept of energy band and your band gap, okay. Different semiconductors have different band gaps. For example, in case of germanium, it is another semiconductor, right. Germanium is another semiconductor, and in germanium the band gap, this gap is around 0.7 electron volt, which is smaller than silicon, you know. For germanium this will be 0.7, which is smaller than silicon. Some materials can have much larger, like 2 or 3 electron volt also, okay, even more than that. Insulators have very large band gap. For example, if I take an insulator, say I will take the insulator and for example I will take aluminum oxide. In that case the band gap might be very large, it can be say 8 electron volt. That is a very large gap. You cannot excite electrons from here to there so easily, that is very difficult, right. So, those are insulators and they do not conduct electricity, okay. The beauty of semiconductor lies in the fact that you can actually change the number of electrons available here, and that will help conduct electricity. So, that is why you can tune the conductivity or resistivity, and you enable all these different wonderful devices, LEDs and so on and so forth, okay. There are many rich phenomena that are associated with semiconductor devices. We shall only go step by step there, okay. We shall only go step by step there. So, you see, when you have an empty band, conduction band here and a fully filled valence band here, and I told you 1.1 electron volt is the energy band gap between these two in silicon, okay. In silicon, it is a semiconductor. Now, there is always something called thermal energy. You agree? There is always something called thermal energy. At room temperature or any other temperature except 0 Kelvin, you will have thermal energy. The atoms will vibrate, there is always a thermal energy associated with it. And if you have read your high school physics, you know that thermal energy is given by kT. You know what this K is? This K is actually Boltzmann constant. I hope you have learned this. kT is the sort of the thermal energy and T is temperature, right. So, let us see at room temperature what is the thermal energy, okay. So, for example, I take room temperature, you know room temperature is around 300 Kelvin, okay. So, what is kT? K value, the Boltzmann constant is 1.38 into what 10 to the power minus 23 SI unit into 300 Kelvin. This is in joule. This quantity is in joule. I want it in electron volt. So what should I do? What should I do? I should divide by 1.6 into 10 to the power minus 19, because this is 1 electron volt is so many joule, right? So I get in electron volt. So I'll see that if I calculate this, I'll see that this is roughly 0.0259 electron volt, or I can say it is roughly 0.026 electron volt, okay, or you can say 26 milli electron volt. This is room temperature energy. So at room temperature, electrons will have this energy, which is 26 milli electron volt. Now 26 milli electron volt, which is 0.026 electron volt, how much smaller is it compared to 1.1? It is very small. And you know, eventually we will learn that many of these processes like exciting carriers, the recombination, the light emission, the carrier dynamics, everything, most of these things are actually exponentially dependent on the energy. Okay. So if you have 1.1 electron volt as the band gap and only 0.026 as the thermal energy, then it is very less probable that electrons would be able to excite from this to that by thermal energy only, right? But you are wrong. Actually it is possible, and there are many things behind this why it is possible. This thermal energy is very low. Despite that, you can excite electrons from here to there. You can excite electrons from here to there. Low probability, but it's okay. We can still excite, okay? And that's why we have to understand the statistics of the distribution. That is very important. So that is a lesson for another class. We shall definitely come very soon, okay? Now, before we move ahead with those, the statistics of how you can excite electrons, even with this low thermal energy, how you will get some electrons here and how you will get current flowing and all these things, we have to introduce something a little different. Everything that we are talking about here was in respect to real distances or real space, okay. For those of you who are from electronics background or who have done your mathematics probably, it's not necessary to know, but it's a good thing to know. You know, if you have a time domain, a signal, you can do something called Fourier transform. I don't know how many of you know it, but you can do a Fourier transform. We don't have to necessarily know it, okay. Fourier transform of time gives you frequency, and frequency omega has a unit of 1 by time or 1 by second. This is second. You need time to understand the time domain analysis of signal, but if you do a Fourier transform mathematically, you get frequency domain signal. It also helps you understand many other aspects. Similarly, a real space, we are talking about centimeter, nanometer, angstrom and so on, right? This is the real space like time. It has a Fourier transform. It's called the reciprocal space, okay. It's called reciprocal space. Its unit is 1 by centimeter or 1 by meter, okay, 1 by distance, and that is useful in understanding many important things actually. That's why we do that. Now it sounds a little bit of abstract, so let's not go too deep immediately right now. Let's go step by step. Most of you know wavelength, lambda, or not most of you, all of you know lambda or wavelength. Wavelength corresponds to even electrons, by the way, because electrons are both particles and waves, you know that, right? So wavelength can be for electrons also. It need not be only for like waves, okay. It can be like particle live waves also. And there is something, wavelength unit is by the way centimeter or meter, that you know. There's something called 2 pi by lambda. Have you come up this term? 2 pi by lambda. You call it wave number probably, I think, right? Wave number. Here in this course, we call this quantity as wave vector, okay. 2 pi by lambda. Do you know what this quantity signifies actually? In a way, this quantity signifies the momentum of electron. We'll come to that. You know momentum, right? Of course, all of you know momentum. You know, this is wave vector, and we call this, you represent this as k. This k is not the same as Boltzmann constant k, by the way. This is just a k. So we can put Boltzmann constant k as kb to represent that it is Boltzmann constant, okay, and this is just k. We call it k, and this is a unit, and this 2 pi by lambda is actually k. We call it wave vector. In some sense, it actually represents the momentum of electron, okay. What do I mean? You know what is h, Planck's constant? Of all of you know that, right? And you know what is h bar? It's the reduced Planck constant. it is given by h by what? H by 2 pi. Okay. You know this is reduced Planck constant, this is h by 2 pi. Now, if I multiply h bar by k, k is this k, okay. What will I get? What is k? K is 2 pi by lambda. What will you get? You will get h by lambda. Now, if you recall de Broglie equation or de Broglie equation, as you can pronounce it differently, h by lambda is what? P. What is P? P is momentum, and this is from your high school physics, by the way. So, h bar k is actually P, which is actually the momentum of the electron, if I am talking about electron as a wave, right. You see, that is why I told you k actually represents momentum, because h bar is constant, no, your h bar is constant. So, constant times k is momentum. So, your k, which is 2 pi by lambda, actually represents the momentum of the electron in some way. Okay, it is the momentum of the electron. Okay, you know what is momentum, right. And you also know that the kinetic energy is given by momentum by 2m, right. So, it will become h square k square by 2m. This is your kinetic energy of the electron. Okay, and if you look at this equation very carefully, right, if you look at this equation very carefully, h square k square by 2m, this is the energy, kinetic energy sort of. Okay, so if I plot, if I plot E and if I plot k, what is k actually? K is 2 pi by lambda. I told you it is actually representative of momentum. Higher the k, higher is the momentum. Okay, if I plot E versus k, what is this? E equal to h square k square by 2m. Sorry, it's looking like y equal to some alpha x square. Do you see? It's a parabola. So, the parabola will look like this. It's a parabola, right. So, the energy dependence on the momentum is actually a parabolic relation, right. Energy dependence on momentum is a parabolic relation. And what is this context? The context is actually of free electron. So, if I talk about a free electron, then this is the energy and momentum relation, which is parabolic in nature. It is parabolic in nature, and this is for a free electron. K, by the way, has a unit of 1 by distance. So, it can be 1 by centimeter. Okay, the K has a distance unit of 1 by centimeter. Okay. Okay. So, this is good. Now, this is a free electron, it is called a free electron, and this is your the energy and momentum relation, very good. But if electron is not free inside a crystal, right. If I take a 3-dimensional crystal, right, a real crystal like silicon, right. If I take a real crystal like this, there are all these atoms there, no, I mean they are periodically arranged, not randomly arranged, by the way, they are all periodically arranged, it is a crystal. If you put an electron there, an electron will move, you apply some voltage and there is a field here. So, you apply a field, electron will move, no, the electron will move. When the electron moves, it sees its surrounding of a crystal which is periodic in nature. It sees a surrounding or an ambience which is periodic in nature in 3 dimension, right. It is a periodic crystal. So, these equations and this diagram, parabolic diagram, it only holds true for a free electron which is free to move in vacuum. In a real 3D, in a real periodic crystal, an electron sees this periodicity that sort of affects its movement or its properties, and so this very smooth parabola that we have here is actually not correct for an electron inside a real crystal. Now, you might ask, why are we trying to study this? It is going to become too physicsy, right. We are talking about energy bands and we are going to study the devices, but we are coming back from energy band and we are coming to this kind of an EK diagram. It is called an EK diagram, by the way, and we are talking about reciprocal space and momentum and energy. What is the relation of all this with the energy band that we are studying, with the actual practical devices like LEDs or transistors that you are studying? The relation is enormous and of very, very critical significance, because these particular energy bands, this is also, by the way, actually an energy band, by the way, except that this is not with respect to x or distance, but this is with respect to momentum or k. All these things will help us understand the basic physics of electron transport and electron properties in a semiconductor, okay, and that is why is the reason why we are trying to study this. Okay. Now, a free electron inside a crystal will not see this smooth parabola in terms of in the sense that it will not have an energy k dependence as smooth as it is supposed to be for a free electron. Okay. So, what we do now mathematically? Mathematically, you have to solve some equations which we are not going to solve here. Mathematically, you are going to solve some equations in the presence of periodic list lattice, right? You have a periodic lattice, right? In the presence of a periodic lattice, an electron might move, right? It will be scattered by these atoms because they are vibrating. These atoms also set up potential. The electrons will be scattered. There will be impurities. There are so many things. So, a real electron, when it moves inside a crystal, has a real world potential there, and so we have to solve an equation in the presence of this periodic potential of a periodic atoms to enable the actual representation of the EK diagram and the equations. Okay. Now, the one simplifying assumption is that all this, it's not an assumption, it's actually true, but these atoms that are there periodically, they set up a potential. Each atom will set up a potential like this, right? There will be a core, there will be atoms, these electrons are there of course, but this is a potential, it's like an infinitely deep potential. And to make things simpler, we will only talk about one dimensional period, no two dimensional. Okay. It's the same thing, you can extrapolate to 2 and 3 later on, but these are atoms that are periodically arranged. All of them have a spacing, all of them have a spacing a. A is lattice constant, it can be say 5 angstrom maybe or 4 angstrom or whatever, right? That's depends on the crystal. So, this is spacing is a everywhere. Okay. My drawing may not be accurate, but this is all a. Okay. So, essentially I am talking about the potential, all of them are potential. Okay. They are generating some potential like this, it is called periodic potential, it is called a periodic potential. I can draw this and I will assume these periodic potentials are nearly infinite, which means I can draw this as like this. Okay. What am I drawing actually? I am drawing the periodic potentials as wells, energy, this energy well, this is a infinitely high potential and this is an energy well, it is called like a quantum well. Okay. So, my drawing is not accurate of course, but these are energy wells. So, we can have a periodic potential which is infinite in number, and electron will move in this presence of this periodic potential well. So, we have to solve and understand the electron movement in the presence of periodic potential well. Okay. Now, you might say that what is the point of all this? The point of all this is that we will be able to understand some very important concept. What on the most important concept is the mass of electron inside the periodic potential. If I take a 3 dimensional crystal lattice, I told you, right, if I take a 3 dimensional silicon, an electron is moving inside the crystal, then the mass of electron inside the crystal is not the free electron mass. Electron mass is, free electron mass is 9.1 into 10 to the minus 31 kg. That is the free electron mass of the electron as it moves through vacuum or free space. But the moment the electron moves through a crystal, this mass will change. Why? Because there are so many imperfections in the crystal. There is the periodic potential. The periodic potential of this atomic arrangement will disturb the electron movement. Okay, it will interact with the lattice. So, this effect, this mass, the electron mass that moves inside a crystal, that mass that it feels is actually different from this mass. It is called effective electron mass. Effective electron mass, and we represent with a m star, and that is different from the free electron mass. And that effective electron mass, how much it is there inside a crystal, what is the value, is the most important thing we need to know the current flows and many other things. Okay. And this effective mass can be understood from this periodic potential that I am discussing about. Okay. So, we shall end the class here today. there's a lot of introduction that we have brought about. So what we shall do in the next class is we'll take from this point, we'll go into where we'll go into the concept of effective mass, okay, and we will also introduce the concept of hole. What is hole? There's something called hole, okay. We'll introduce the concept of effective mass, we'll introduce the concept of holes, and then we will also introduce the concepts of distribution of electrons, okay, distribution of electrons, how electrons are distributed in valence and conduction band. You remember this diagram that I keep drawing here, this diagram, right? This is conduction band, this is valence band. How electrons are distributed here, how many electrons are there, how many electrons are here, all these things depend on statistics, okay. It's called Fermi-Dirac statistics. So we shall introduce the concept of Fermi-Dirac statistics in the next class, okay. Introduce the concept of Fermi-Dirac statistics. We will also introduce the concept of effective mass and holes. What are holes? And those will help us basically go ahead with the third lecture where we introduce doping and other things, okay. So today's class, what did we recap? We should have a quick recap for 1 minute. Today's class I told you that semiconductor devices are very important, they are the most important probably, you know, in the electronics industry. Everything depends on semiconductor devices. So many types of semiconductor devices that are there that we may not be even aware of, right. And it has had a long history from 1948 when first transistor was invented in BJT, I mean, and to 2018 when we have transistors at the scale of 14 nanometer, 10 nanometer, you know, it's a very sophisticated platform now. Moore's law is there, and the scaling of transistor has continued over so many years. But this is not transistor only for your processors or chips that go into laptops and cell phones. There are many other transistors which are not scaled up because they are required for RF power or radio power, you know, radio frequency power application. Those do not scale like this. There are many kinds of transistors, or LEDs or solar cells do not scale like this. There are many other devices there, right. We talked about bands, what are energy bands and how do they come about. There are different kinds of semiconductor I told you, and to introduce the concept of band I told you that you have to go to a single atom. We have to talk about the discrete energy levels. The moment you start bringing the atoms close together, these discrete energy levels will split up. They'll split up to form some bands, and these bands will give you band gap, and that's why you have a highest filled band, a highest filled band and an empty band here. They're separated by an energy band gap. For insulator this is very large. For metals there are no band gaps. For semiconductor this band gap is appreciable, so that you can actually excite electrons from the fully filled valence band to the empty conduction band, and by doing that you can increase the conductivity or resistivity of the material. That's the beauty of semiconductor, you can tune the conductivity. And then we talked about electron volt, the concept of electron volt, how much is the energy. Silicon and germanium and different materials have different band gaps. This is dictated by many properties of the material. And finally we came to in the reciprocal space, I introduced the concept of 2 pi by lambda as k, which is sort of a momentum. Actually 2 pi by lambda is this k is a sort of a representation of momentum. I told you that Ek, the diagram or the energy and momentum relation, is a parabolic relation for free electron in vacuum or in space. And I told you that the moment electron is put inside a real crystal like silicon or germanium or so on and so forth, the periodic potential will basically affect the movement of electron, and so the mass of electron as experienced inside the crystal also changes. We call it the effective mass, okay. You please recall that all these atoms that are there arranged periodically in a crystalline solid set up this periodic potential, and that's why the periodic potential distorts the movement of the electron, and that's why we get this different effective masses inside the crystal. And that's why the concept of energy band gap actually arises only when there is a crystalline solid, because if this crystalline or the periodicity of this distance is not maintained, then you cannot solve the equations. You cannot actually get, practically speaking, you will not have a periodic potential, and so you cannot have a uniform band gap also, okay. So we'll end the class here today, and in the next class we'll continue with the concept of effective mass. We'll introduce holes. Electrons are as much important as holes. Holes are also some kind of quasi particles that carry current, and we'll introduce the concepts of, if possible, doping, and before that distribution, Fermi-Dirac distribution, that will tell you how electrons are filling up the bands. How many electrons are there in a semiconductor, what is the probability that electrons are there, and how many electrons are there. All these things are captured by Fermi-Dirac statistics. And then we introduce the concept of doping, and by doping you can actually change the conductivity, okay. The other approaches are, for example, by shining light. That is a different thing that is used for photodetectors and solar cells, but without light you can also change by adding some impurities called doping. So those things we'll try to introduce in the next class, okay. We'll also try to correlate with practical applications, as I keep telling you in the beginning, how these devices correlate with practical life examples, right. We shall have that in mind so that you do not lose track of that. Okay. So with this we'll end the class today, and I'll hope to see you in the next class where we shall discuss about effective mass, holes and Fermi-Dirac distribution. Okay. Thank you.